stop sharing. So from now on, payment, you can go ahead and share your slides. And during the first minute of your talk, I'll make others posts as well.
All right. So my microphone is off. Is it okay?
Yeah, you can ask if those online here, but I think they do.
Okay. Good. So hello everyone. I'm Payman. I was asked to explain a little introduction to linear differential equations because I guess you guys are not taught in the chemistry department. But so this is a very oversimplified introduction because most of the mathematicians spend their life on differential equations, special partial differential equations. So I just put a very simple introduction here. So let's begin. In mathematics, we try to explain the relation between different actually parameters and variables in something that we call equation. The explicit equation examples are like Newton's second law or mass energy equivalence, which are really famous. But this kind of explicit definition and relations, unfortunately, are really rare because nature and reality they are really complex. So we have no choice to define the relation based on rate of the change of variables. If an equation contains the change or rate, whether with respect to time or location, we call it the differential equations. The famous examples is the fixed second law, which is describes diffusion with respect to time and location, and also Schrödinger equation. In Schrödinger equation, as you probably all of you have maybe noticed, some part of the Hamiltonian actually contains the differentiations which explain the location of the electron. So in most cases, we cannot solve these equations directly. We cannot find that function that satisfies the restriction explained equation. So we need to use numerical method. But before going into the actually some details about the solution, I need to define some terms and definitions here. So first thing is order. Order is the highest derivative that is mentioned in the equation. For example, in the first one, the order is the first example explains the first order equation, and because it only contains the first derivative, and the second one is of course the second order because it includes the second derivative. The second term is degree of the equation. The degree is the highest power of the highest order in the differential equation. For example, in the example that I mentioned here, the order is 6 because the highest order, the highest derivative is 6, but the degree is 4. And we have other definitions, ordinary differential equations and partial differential equations. Ordinary differential equations only includes one independent variable. For example, in these examples, which shows the second order equations, the only independent variable is x, which y as a function depends on x, which is only one variable. But in partial differential equations, we have multiple independent variables. One example is diffusion equation that depends that concentration C depends on time and also location. And a solution is a function that satisfies restriction defined by the differential equation. So our goal in differential equation is to find that function, which in most cases we have no choices using numerical methods. But here I want to find the direct solution based on the algebraic functions. So first order systems of differential equations actually are type of equations that we can find the explicit equations as solution. The general form is the system of the differential equations that in which the variable is explained by different function, and we only have one independent variable, which is t. But for finding the explicit solution, we need to oversimplify this general form, which in next step is explained as linear system. In linear system, there is no multiplication of the functions. For example, as you see, in the linear system, we cannot see any multiplication between x1, x2, etc. So we, as I mentioned some examples here, examples of linear system, as you see in the first example, that has constant coefficients, and we easily can solve this equation. As you see, the x and y are explicitly expressed explicitly as trigonometric equations. But in the second and third example, as you see, for example, in the second one, it is still a linear system, but as you see, the coefficients are not constant. We can see the t as an independent variable in the coefficients. And also in the third example, as you see, it's not even the linear system. We have a multiplication of the different functions. And the solution of these systems are very complicated. We cannot find the explicit solution for these things, so we have no choice for numericals other than numerical solutions for these systems. Here, I only focus on the linear first order systems. So linear first order system, as I mentioned, can be explained in the matrix and vector representation. If the B vector is 0, we call the system homogeneous first order system. So it's another step of the simplification of this system, but also solving this system is also kind of complicated. At the last step, we oversimplify the system as a system with the constant coefficients. So A matrix is not dependent on the t variable, and all the coefficients are constant numbers. So at this stage, we are able to solve this system based on the steps that I'm going to explain. So first of all, we need to find the eigenvalues of the A matrix, which is based on we need to solve the determinant of the A matrix minus lambda identity matrix. By solving this equation, we obtain the lambda, which explains the eigenvalues. After we obtain the eigenvalues of the system, we can actually obtain the eigenvectors. Having these both parameters, we can explain the solution of the system based on the following, based on the equation that I mentioned at the bottom of the page. The system easily can be explained as the summation of the exponential function multiplied by eigenvector. So in the following slide, I put an example. So as you see in this linear system of the equations, A matrix, as I said, it includes actually A matrix the constant values. So first of all, we determine the lambda values based on these determinants, and then after we obtain the lambdas, which here it's -1 and 4, we easily can calculate the eigenvectors, and based on the previous equation, we easily can explain the solution of the linear system. But there is one exception, because in some cases, lambda could be complex. For those who do not know the complex numbers actually are numbers that contains the negative square of 1. So we represent the negative square of negative 1 as I. So if you solve the determinant and obtain the complex number, we need to add some trigonometric functions to our solution. So beside that exponential function, we need to actually multiply trigonometric functions for obtaining the solution. And it's based on the following steps. So lambda is expressed as alpha plus I beta. As I said, I is the square of the negative 1. A square root of the negative 1. And the eigenvector is explained at R and S. The general solution of this system is expressed as the following equation. So first of all, for this example that I mentioned here, I obtained lambda, which is -2 plus minus I, and which means alpha is -2 and beta is 1 here. Then based on the lambda, I obtained the eigenvectors. And following the equation, we can easily find the solution of these linear differential equations. So I guess that's it. Please let me know if you have any questions.
Okay, please join me thinking. So any questions, especially from those who yet look forward to take differential equations? Or maybe catching any errors from those who don't. Anyone?
Finding the eigenvalues, that's using the Wronskian, right? Or just a Wronskian and something else.
Using what?
It's called the Wronskian.
Wronskian.
Yes. Wronskian.
I'm not sure what you're referring to, but you're asking about how to calculate the eigenvector.
Yeah, it's taking the determinant.
So eigenvector, let me show the equation. I think it's so here, as you see, determinant A minus lambda I. The next to it is another equation.
Yeah.
So after you calculate lambda, you can use this equation for calculating the vector, the eigenvector. Is that your question?
We looked it up. The Wronskian is
Oh,
something else. It's
Oh.
two equations. Thank you, though.
Questions? I do have one type, but I can verbalize. So in your last slide, you showed that solution for system of ordinary differential equations with constant coefficients may have exponentially growing or exponentially decaying character, or it may have oscillatory or combination of both.
Right.
So which properties of the A matrix you tell us for sure that it will be only decaying or only growing or only oscillating? Just intuitively, it's not a...
Oh, that's a great question. So which one is related to decaying and which one is related to harmonic of the A matrix? So as I see the...
Because your example clearly shows it.
So the lambda, of course, is related to the decaying. But I'm not sure.
Okay, what about, if you can say about the matrix, can you say something about eigenvalues? Which eigenvalues provide oscillatory solutions and which eigenvalues provide growing or decaying solutions?
The eigenvalue is explained is related to the exponential function. The values
Yes,
that are
yes, but it's like imaginary exponential oscillates.
correct. Yes,
I'm talking about real exponential which grows with the case.
oh yeah, of course, based on this equation, so of course alpha, which is the first part of the real part of the actually eigenvalue, explain the decay,
Mhm.
and the imaginary part explain the harmonic.
Okay, so if all eigenvalues are imaginary, then it will be only
It's
harmonic.
only harmonic. Yeah, that's
That's
correct.
further behavior.
Correct.
And if all eigenvalues are real,
Real,
then it's only growing with the
exactly.
So this property will be observed in the solution that we find numerically. Sure. More questions to payment? Questions, well? Questions for the thank you. Or even let's teach us what it is.
I am William, and I'll be showing you guys if when we find out if the density matrix is time dependent or not. So to get some out of the way, we don't see rho right now, but that is what our density matrix is, which is our wave function and our wave function, the complex conjugate of it, and these brackets right here, we have our bra and our ket. The ket value is going to be our like our column vector, while we'll have like a row as our bra, and then A is just part of our operation of an ABCD square matrix. So when see if this is time dependent, we'll take the derivative with respect to time and see if it equals 0. So just deriving it, we have to make sure that we apply product rule. And then when doing that, we can see that the middle term is killed by time derivative of A. So A dot be killed because it's just a time derivative of an operator. So an operator is dependent on time, obviously. And then once applying our derivatives, our H is our Hamiltonian, just from taking the derivative. And then we end up that getting the I over H bar, the conjugate times H minus A minus AH times then our wave function again, which can be then, but one way that you'll commonly see it is this notation on the bottom, but these last two parts are the same thing. From here, from this first part of what I'm presenting about is that these two matrices, matrices are not commutative, but there are a select few that are, especially if one of them were to be the identity matrix, and then there's other few examples where two matrices are commutative. And so this, since it's not always equal to 0, this means that it is or can be time dependent. And then connecting this to the quantum Louisville theorem, our density of time, we pretty much get this exact same thing again, but it looks slightly different. And you'll commonly see it as our bottom part, you'll commonly see it as 1 over IH bar, which all they did was multiply the top and bottom by I. And then just trying to find some connections between these, between different things, we're able to see that what we originally started off to is actually the trace. I don't have the trace part written out, but the trace of our A matrix times density with their density. And then the trace, if you don't know, is just taking the sum of the diagonal elements of the matrix. So if you have a square matrix of like 2, 4, 5, 6, you just take the 2 and the 6, 2 and the 6 together. And that's what I had.
Okay, please join me in thanking Julia. So any questions from online or from the audience?
So I guess just to text up. So you talked about the time checking if the operators are time dependent. Is that needed to, I'm assuming that goes to the same tools you use to see if the density matrix is time dependent?
Yeah, if the operators, if you took the derivative and see if it was 0, if it's 0, that means it's not dependent on time.
So the density matrix is operator, or I guess matrix.
Or the A matrix is the operator. The density matrix, the actual density matrix is this next to the row.
So density can be considered as an operator. And if you follow this Heisenberg equation motion. So there is something in the chat.
It would be correct to say that the change in time expectation value of an operator is determined by the commutation of the operator Hamiltonian operator.
Just say yes.
Yeah.
It was set up. Okay, there's a question from Robert.
So it's safe to say that Louisville equation is a way of representing the density matrix. Yeah. It's a lot of just saying the same thing, but I just wanted to make just kind of put it in your face that that connection was there.
Okay. Any other questions? Thank you for including. Can you go back? Can you go to your last slide? The second last, just yeah, this one. So I don't know how to formulate it as a question. I just wanted to bring in the information. The scenic goal of quantum theory and theory at all is to serve the experiment, to predict outcome of measurement. And this bracket, this operator inside, is the practical way to compute an observable. But there is an alternative way. One can get an expectation value of an observable either from wave function or from density matrix. And it is the reason why later on we, well, it's not only the reason, but it is a condition that allows us to jump from wave function to density matrix. Yeah. I don't know how to formulate the question, but if anyone disagrees, please raise hand. Okay, more questions to you.
That y star c dot or plus? Y star c times x star b or y star c plus x star b?
That's just to say that as part of the conjugate wave function.
Yeah, but it should be plus at middle. It's not a multiply.
No, it's not a multiply symbol. Yeah, David.
Why in your drawing, why do you have the star written there?
To show that it's conjugate.
It's already
It's
conjugated.
already a conjugate without that.
Well, it's just showing that to represent that it is.
You don't need to.
Yeah, in standard notation, one do not need the star in the bracket. That's correct. Thank you, David. So more questions one, more questions two, more questions three. Let's thank you once again. And now, Landon, would you like to share your slides? So I think this talk will be most intellectually challenging. It was challenging, difficult to compose, very dense, and it will be maybe difficult to follow, but it will be mostly useful. So there will be a combination of previous two and setting up a bridge towards practical computations.
I think that I'm gonna need to close Zoom and then open it again. Yeah. I will be right back.
So,
Yes, I can switch out this.
just to fill the pause, I will sketch some funny pictures on the board so that you do not feel bored while Landon is preparing. Huh? What? You can. So at the end of his talk, he's going to maybe in a different language to set up an differential equation for the object of density matrix. So on the left it's time derivative, on the right it is matrix which will control all the change in time. So the elements of density matrix give us populations of orbitals, and we mainly track only populations, but there are also non-diagonal elements which control coherences. And Landon will try to make a bridge between what previous two speakers told about density matrix and differential equations, and tell what do we have in the elements and how do we practically solve this equation. And is Landon already there? Yeah. Okay. I'll finish shortly. So here I do show the density matrix for system with only two orbitals, one and two, right? And it already has 4 elements, which is too much. And the super operator that controls its evolution is too big. So what we are going to do, and this is a part that is always skipped and not covered in papers, because it is a practical trick that helps to do things quickly. So one focuses only on segment of density matrix and super operator, which are highlighted in blue, which deals only with population. So we focus only on population of first orbital, population of second orbital. And then the elements that will control their evolution, which in brief summarized as a Redfield tensor, and for large practical systems that which we do as a computation, this matrix is like 100 by 100. This element is just for 2 by 2 as an oversimplified example. Okay, let's listen to Landon because his talk is more interesting and more important. Landon, floor is yours. Sorry for holding the audience. Your microphone seems disabled.
Okay, there we go. Can you hear me now?
Yes.
Good. All right. So yeah, I guess this is kind of a little bit more on the theory here. So this is basically a bunch of the relevant equations. Some of these are just sort of different versions of looking at the same thing. So like this equation here is the same as this equation here. And yeah, like it's kind of color coded so you can sort of see all the differences. But yeah, this is just shorthand notation. So once we have our density matrix, we want to figure out the time evolution of that thing. And so that essentially means that we need to solve this guy right here. And so we can sort of reduce this into a like eigenvalue eigenvector problem, because like this is what we're after, right? It's equal to this, and that is equal to this, where these are basically our eigenvectors. And so what we're really going to be solving is this guy. Yeah.
Okay, can we stay on this slide a little more?
Yes.
To speak additional things. So the top blue box agrees with what William was teaching to us, right? So it is
Yes.
evolution of density operator. And here in this limits, as it is shown in blue box, it is absolutely equivalent to Schrödinger equation, to evolution of wave function. There could be translation one-to-one. And this deals with first level of quantum mechanics where all systems are assumed isolated. So if one creates a system in the excited state, in eigenstate, it will stay there forever. But there is a little cloud on the upper right. So the density matrix of the world is a direct product of the density matrix of our system of interest, which could be like a set of levels, and the density matrix of the rest of the world, which sometimes is called bath. Landon, will you please go to the very first slide, which we borrowed from Aaron's paper? This is a nice picture. Yes. So the system is considered swimming in a bath in a sense that it's just a figure of speech. The system is immersed in a thermostat composed of the rest of the world. Okay, can you go forward to your...
Maybe. There we go.
Yeah, okay, thank you. And if we recognize that our system of interest is not isolated, not alone in the world, if it interacts with a thermostat, with a bath, then equation of motion for density matrix is not restricted with a blue term. It has an additional term which depends on density matrix of bath, which is green here, and interaction between system and bath in the second order, which is shown as V here. So this V is if the bath is the thermal motion of the ions in your molecular system. If the interaction between electronic primary system and the bath is non-adiabatic coupling V, then the equation of motion for density matrix, which includes populations of orbitals, will include this term. And this term in brackets is equivalent to Redfield tensor that we worked on in previous meetings. So in a shorthand notation, this long equation can be stored as time evolution of density is Liouvillean dynamics plus Redfield term of dynamics. And this density operator can be replaced, can be expressed, can be cast in terms of a specific basis in the basis of basis functions psi I, psi j, and then the density matrix in the basis is density operator is composed as matrix times this basis set. So our problem of following the dynamics of density operator in a specific basis is a system of differential equations, where we have differential equation for each of these row ij. While for practical purposes, we are interested only when they coincide, row I. But there is also very interesting science when they do not coincide. It's just too much for us right now. Now, we do have differential equation. We can technically propagate it by infinitesimal time increments and see how each of elements changes in the next time. But then it is numerically more demanding if, in case our L plus R operator, which was named like A capital in the first talk by Payman, if this operator is time independent, then one can use the solution based on the eigenvalue problem. So one can find eigenvalues and eigenvectors of this L plus R supermatrix, and then compose the solution based on them. So the lower line shows how the solution is composed for a specific initial condition. Because if you do not care about the initial condition, then we have infinite number of solutions and we do not know which of them correspond to real life. Okay, Landon, sorry for interrupting. Please go ahead and continue.
And so this is kind of a breakdown of that equation that we were just talking about. So I guess this is that initial condition that Dimitri was just mentioning that actually, sort of solidifies our solution so that we have, the one particular solution instead of infinitely many of them. And then we're basically just, expanding that using all the other eigenstates, I guess. And I guess this is how we actually propagate it through time with this exponential here. But yeah, this whole thing, each of these terms just winds up being a particular expansion coefficient, like the C whatevers, if you've taken like quantum mechanics classes.
So,
yep.
Go back.
Yep.
Let me add a comment. One more back. Yes. So let's look on the lower right blue box with eigenvalue problem. So now we connect back to the presentation by Payman. So depending on the real or imaginary character of the capital omega of the eigenvalues, we will have either oscillatory or, as Payman told, harmonic solutions, or relaxing or exponentially growing solutions. So the L operator, Liouville operator, explicitly has imaginary union, which means it is responsible for oscillatory solutions. And relaxation Redfield term, as we have seen practically in your numerical data, has only real values. So the density matrix here in our practical calculations is expressed in terms of eigenstates. And if it is in the terms expressed in terms of eigenstates, then Liouvillean dynamics do not change population. So if you focus only on the populations, all Liouvillean terms are dropped. And we have only R terms, which are real. So in our practical computation, the omega capital, the eigenvalues are real, and the dynamic that we observe is either exponentially growing or exponentially relaxing. Okay, Landon, sorry for interrupting you once again. Please go ahead.
Okay. So when we actually get into the file, I guess this is just a few input parameters that you should be aware of. So the time steps, you're going to want to set that to like however many of those, PXXX files that you have. And then you're also going to want to set the O min and the O max to whatever range of orbitals you're actually trying to observe. So like in this case, if we're trying to get data on like what would this be, like 30 orbitals roughly, then you'd set your O min and O max appropriately so that you're only looking at that range. And so this is kind of part of the, some parts of the code where we're actually utilizing the Redfield tensor. So these are all like in order in the code also. So this is sort of where we first define them, and then these things are just straight up imports of the Redfield tensor. So basically you're just looking at, the conduction band here, valence band here. And then as the code goes on a little bit, we basically wind up setting, everything below the main diagonal to 0. And that's just to, disable thermal excitations, I guess. I'd have to think about that more though to actually be sure. And then we also, we also wind up manipulating the terms along the main diagonal later on as well. And so this is sort of the Redfield tensor for electrons. We wind up diagonalizing that into the eigenvectors and eigenvalues, because those are, what we're using to actually solve for the time evolution of the density matrix. And then we get these C terms, and then we wind up using those to solve for this equation down here. And this one also updates that same thing. And you can kind of see, what all of the terms sort of are that we're using in this case. Yeah. And then otherwise there's just a bunch of stuff in here.
Okay, please, Landon, are you going to show anything else?
No, I do not have anything else.
Okay, then please join me. Thank you, Landon. So any questions or challenges in the room? Any questions? Yes.
I guess I have one question on the second slide about the row bath term.
Okay.
So that's gonna be a matrix, right? And then how would we go about determining that, I guess, in a way, or estimating it?
Landon, please try anything you want or can, and then I'll pick up and continue.
I mean, I don't know off the top of my head how we calculate that one. Because I mean, ultimately it comes from the nuclear motion, but I don't, yeah, in the code, I guess I don't know how we actually get to that. Well, I mean, ultimately, I guess we sort of recast this equation into this form more so. So we kind of, I guess, go around it in a sense. At least I think.
Okay, yeah, thank you, Landon. Joseph, you are giving all of us tough questions, and they are right to the point. You were asking it at the end of previous meeting when everyone left. So by logic of these derivations, we assume that both system and path are quantized. So that any degrees of freedom are just set of quantum levels, which immediately contradicts to what we do practically, because our path, our nuclear motions are just sets of ionic positions which perform some motion. So we do it, it's a four-span argument. We cannot quantize 300 degrees of freedom. So if you do fair job, if you do everything as it must be, then each nuclear degree of freedom and each photon degree of freedom, each photon degree of freedom is just a set of harmonic oscillators, set of levels, multidimensional oscillators. And then those oscillators are considered to be like thermal bath in the stove thermostat. So they consider to have no coherences of diagonal parts of the matrix, and Boltzmann factors energy to the power e to the power minus energy divided by temperature in the denominator. And then by combining this Boltzmann factors of the thermal bath and interaction with electronic degree of freedom, we will go relaxation terms. If we have non-quantized point charge ionic motion, we do a lot of force-man arguments. We artificially, you need to artificially add period belts to promote relaxation only in one direction, or balance excitation and de-excitation. And there are several tricks. So this question is not easy. And what is shown here is abstract, ideal, and non-practical. Thank you for picking. Any other questions to Landon? On the chat line?
So Dimitri asks, what is psi naught and how is it composed? I believe that is the same thing as psi of 0 here, or well, yeah, rho really, I guess. Where did it show up?
Yes, here in this, we do not need to see anything else than this slide. The slide is excellent. So your matrix U is a matrix that composes all eigenvectors.
Yes.
And C lowercase is matrix of expansion coefficients, which are, yes, you're correctly labeling. But what is psi naught? And if anyone is watching on the code, if you will not show it right now, maybe during the rest of the session, if anyone can pick up lines of the code that define psi naught, please do.
Yeah, I can't remember if I grabbed that one or not. I guess when I was, nope, I didn't.
Okay, let me try from the top of the head, but it's better to show exact code. So,
well, I could just try to find it, I guess.
just psi naught equals to.
Got too much stuff on my screen. Something to do with the holes.
Yes, for electrons, let's move for this PPH. Backwards. Okay, yeah, let's stay. Yeah, stop here. Very good. So these two lines, 184 and 185, makes build as a bridge towards the next few talks. So in the next few talks, we will all look on the importance of the input parameters IE and IH, which tell from which orbital we remove electron and to which orbital we promote an electron. And this PP and PPH, comma 1 means what is the initial density matrix, or segment of density matrix responsible for population at time step 1, which actually time equals 0. I don't know if I can count it. So the psi naught is the segment of density matrix at initial time, which has only one element equals 1 and all others are equal 0, which corresponds to populating only one orbit. I don't know whom to ask if the author of the question is satisfied because I asked myself. Landon, are you satisfied with this answer?
Yeah.
Okay, thank you. So more questions to Landon? Questions 1, questions 2, question 3. But thank Landon. And next presenter is Adam. Adam, would you like to share your screen?
Hello, yeah.
Oh, thank you.
All right. So here we are. All right, I'm just going to talk about the input files and some of the parameters that you need to change the Redfield MATLAB script. I was unable to get this working on my own, so maybe I could troubleshoot after the meeting. But you require 5 or 5, I guess, files to do this. You're gonna have your triple R file from your correlation script, the output, your energy pop, you should have that as well, for the correlation script as well. And then this Redfield script is the main script that we're going to be looking at. You can find it in bin, which is in Korean. But these two down here for master optics and out, we need the script is going to need these to run, and getting them is it's not exactly apparent. So for master optics, it's syntax that's used in the script, but it's initially generated as for master equation in your optimization directory. So you're going to edit your input overlap to contain your desired orbital interval. You're going to run this script. When I ran it, it did not generate working files. So this may be incorrect, or I did something incorrect along the way. But this obtains your for master equation file, which can simply be changed or copied to for master optics. Band out just requires you to run another FOSP job to obtain those partial charge densities. That's a pretty quick job typically. It's going to use this in-car PC and your concar from your optimization. And when this is finished, you run this integration script like we talked about a few weeks ago. And then you're just going to edit this to fit your orbital interval. And then you're going to run this as a Perl script. Band out is just obtained as one of the output files, and you can copy this to your personal computer. So in the MATLAB script, this is in the Redfield script, like the other script, you're going to just need to change this Homo, this Omin, and this Omax, like I talked about before. That's just whatever your energy pop specifies. We talked about that before. But you're going to get a number of different figures when you run the script. This is going to be one of them. This is going to show Fermi energy and of the electron in the hole, and over time. You should have new output files after you run the script: CT as states and DEV, HEV, E. I'm not sure what those quite do, but I think I do have some idea. But questions? That's all I was really able to gather.
Okay, please join me in thanking Adam. So any questions in the audience? Any questions online or in the chat line? So it was all crystal clear. Adam, can you go a couple of slides back?
Yep.
More? So, no, forward, the image.
Oh, the image, okay.
So can you please tell a little bit more about this image? How does it relate to solution of the differential equations for populations of orbitals? We will keep talking about it. Several talks will cover it, but just give us a little bit more introduction. Just anything you or know or want to know about this image.
It's a hard. I'm not exactly sure how to answer that.
Based on the basis that was provided to us by payment, do you see oscillatory or relaxing dynamics?
It looks relaxing, yeah.
Okay, so nothing oscillates. Okay, it's good. So what is yellow? Okay, what is yellow stripe and what is blue stripe?
Yellow stripe is going to be the hole, and blue is going to be electron, I believe.
Or opposite? Who cares? Right?
Opposite. Oh.
And what what is the initial condition? That
The initial condition.
your IE and IH, can we learn it from this diagram? What was the initial condition?
It's specified in the initial part of the script.
Right, but what if you want to, if you would try to hide this information from us and show us only the blue, this greenish figure? Can we extract your IE and IH just looking at the figure?
Yeah. So it's I mean, the difference is going to be. It's the Fermi energy between them should be, or the difference between energy and Fermi energy should be 1 in the initial.
So how this image would look like if you would start from IE equals 1 and IH equals 1?
It would just be, would it be 0.5 or would it be? I'm not sure.
No, you started showing in the right spot. And I feel that you are thinking in the right direction.
Here?
Yes. Okay. Can you go to the editing mode and we will just add some annotation?
Oh, yeah.
So let's go to draw. So right now you started from IE equals 2, right?
Yeah.
And then at the end of dynamics, it approaches the LUMO, which is IE equals 1, which is equals to. If you would start from IE equals 1, then your yellow stripe would go at this line, right? And with your initial condition, we see how the system jumps from LUMO plus 1 to LUMO, right? So it's an event of relaxation.
Yeah.
Okay. I'm happy. Other more questions in the audience or online or in the chat line? So questions, more questions. One.
I have a question.
Oh, please, Amir.
For which kind of material did you plot this figure, Adam?
So this was the this was just the materials provided for us. This was not my system. So this was the just with the files presented.
I see, because I had the question why electron relaxation is faster than the whole in this system. But okay, since it's not your research, that's fine.
So the credit for this data set goes to Keya. So it was data set from her paper, and maybe if she wants, she can answer or just postpone the discussion. But the system here is the single oligomer of conjugated polymer, like cis-pol, etc. I mean, does it partially satisfies your curiosity?
Yes, because I saw such that behavior also for PCBM systems. Systems including PCBM, but do not have a solid answer for that right now. Why whole relaxation is slower than the electron relaxation, such that systems.
Yeah, we can keep digging in this direction, but maybe it is a common feature of conjugated organic systems.
For those systems based on non-fullerene acceptors, I didn't see such that behavior.
Okay.
Whole relaxation was faster, but for some excitation, I saw such that behavior. We can discuss it maybe later. By the way, thank you, Adam.
So let's count down once again. More questions to Adam 1, more questions to Adam 2, more questions to Adam 3. Let's thank Adam once again. And I believe the next presenter is Judith. Share my screen.
All right, so kind of like, as we've been kind of talking about with this code, we have these IE and IH parameters and this density matrix. That's kind of the whole deal of what we're trying to figure out. And then as Adam was talking about, we have our input files here. So I won't go over that. For my model, I am running bands 347 and 376. And just one other thing to watch out for in the for loop for the band integrate. You do want to watch out for changing these numbers and make sure that you notice that it's a less than sign, not a less than equal for the upper band, because that might screw you up. So the way that density matrices are represented, as we were talking about. So we start by offering these parameters IH and IE, which actually I'll skip ahead a little bit. Basically what they are counting is the band number you are away from the HOMO or LUMO. So for the initial hole, it's counting the number of bands below LUMO you are, and for the initial electron, it's the number of bands above HOMO. And so that's just kind of highlighted here. So then back here, what we have is this initial, an example of an initial density matrix for the electrons, where the time step may be the columns, and then each different orbital or band is the rows. So we're starting out with a electron all the way excited in band 4, I guess, above HOMO. Over time, this will get evolved, I guess, and fill in all of these extra zeros that you see past time t equals 0. And that's just using this code snippet on the bottom, I believe. For the size 0, that is used to calculate some of the coefficients, as Landon was talking about before. And that's just the first column of this PPE matrix. And then I guess for the holes, it's basically the same story, just kind of reversed, because then you're counting down from LUMO. Once you decide to put whatever IH and IE you have, we have this similar sort of graph that Adam was looking at again, which is just showing the energy of the holes and electrons over time, along with like their relative densities based on the color. So as we can see here, we have the hole exciting, I guess, and the electron relaxing, as we would expect. And that is all I have.
Okay, please join me in thanking Phil. So any questions in the face-to-face room?
This is just more a question about the code itself. Whether you have it set up for the excited states, give you one less orbital, since it has to count the flow as well.
Yeah, I guess because you would have to like count over that, so it won't necessarily be.
It'd be 8 down and 7 up. Or 7 up from the LUMO.
Yeah, I guess like in this code, it will be 8 up from the HOMO, and then it will be 7 down.
So notice like how he has it described, where he has the IH related to HOMO and the IE related to.
Yeah, but the IE is counting from above HOMO, so it would be counting LUMO and then 7 more up.
Yes,
Yes.
that's correct.
IH would be counting 8 down from HOMO.
No, you notice he has IH related to LUMO, not HOMO.
Yes, you start at LUMO, not HOMO, so then they have like a little bit like overlap in the HOMO area, I guess.
Great question. Thank you, Stephen. Joseph, can you please go one back? Yes, here. So initial condition that we were discussing is one, say no. So here it shows IE equals 3, I think, for Homo plus 2, right? So if it is, if you want technically to try IE, if you want to start from Homo, we have a trivial dynamics with no dynamics. Matrix indices by convention do not accept index equals 0. So it should be natural, like amount of apples. It cannot be 0, right? Therefore, we make this offset by 1. Still, does it make sense? We do have a question from Lola in the chat line.
How do you decide what to select as your IE and IH? So, it's a great question. So you'll start probably by looking at the oscillator strengths between like kind of all combination bands that we would get from when we calculate the absorption spectra. And then you basically would want to start looking at like the highest oscillator strength transitions. And that will be like the most likely states or transitions that you would expect to happen. For this example, I didn't necessarily follow that rule. Kind of like Adam was mentioning, there was a little bit of a problem with the code that I wasn't able to figure out. So if I made my hole too low, then I would get a kind of odd sort of energy graph. So this one is just kind of almost like a random set of IE and IH that produced a nice looking picture.
Oh, are you satisfied with the answer? Okay, yeah, thank you. Awesome. Okay, more questions to Joseph? Questions 1, questions 2, questions 3. Let's thank him once again. And next presenter is Kamrun Nahar Keya. Yeah, would you like to share your screen?
Yeah, sure. Are you able to see my screen?
Yeah, we can see your slide.
So today I will show how to do the Redfield change the parameters when we need to do electronic dynamic calculation. So for that we need this MATLAB file, so which is available in a bin directory. So for doing the calculation, we need energy pop for master optics RR file. And our previous speaker, they actually explained those things, how to generate for master optics and RR file. We already generated when we did the coupling calculation. And the person also shows that how to generate band out also. Okay, so here in the MATLAB file, we need to change the Homo orbital according to the system you are using, and then you need to change Omin, Omax. And we can see that there is one thing like Z steps and Z size. So Z size you are able to see from the postcard file. You need to edit that one, and also the Z step is you are able to find from the size of the band up. And these are the important things, and these things I just add, but it also shows already that how to generate the purchase file run, and purchase file will be generated. And if we check the purchase file, we are able to see that in a Z direction, we have the size is 126. That's why I'm using that one. And if we want to see, like, if we check the band out, inside what's inside, we are able to find that there are 126 orbital inside.
Okay, not orbitals, but grid points, right?
Sorry, grid point, yes. Not orbital. Orbital is different. Yeah. So what the hell? Yeah. Yeah, so you can see in this figure, like because we use 600 and 600 time steps. So when and because we use we started from orbital number 5, that means LUMO plus 4, and in this figure actually shows where electrons are located. So if we like see this one after rotating these figures after 600 time steps, we can see how electron are transferred to different orbitals. So we can see the different shapes because of they are transferring the electrons. And another one, and this figure, like this one basically is better. Oh, so this one actually shows that because we start from the LUMO plus 4, so we can see in that in a 5 or orbital 5, that charge density is in the at the edge of here and at the end of this position. And after that, the population actually jump from 5th orbital to 4th orbital, and then again it jumps to another orbital, it jumps to 4th to 3rd, 3rd to 2nd, and then and first orbital. So you can see that in the 3rd orbital, there is a big, large peak in the middle. Actually, it's not. It's, we can say it's a middle position, and in this way we are able to see the charge transfer of the system. Yeah. That's it.
Okay, please join me in thanking Kayla. So any questions to the presentation from the in-person room or from online?
I think someone sent message. Not creating but processing purchase file to, okay, processing, yeah, processing and purchase file to generate the banner.
Okay. So this talk goes along with what we discussed before, right?
Yes, yes.
So let's count down more. Any questions, additional questions to Kia 1, questions to Kia 2, questions to Kia 3. Let's say for once again. And those were data for new system, right? For tightly packed polymers.
Yes, yes.
Okay, so the next speaker is Amara. Amara, would you like to share your screen?
Yes, sure. So I'm going to talk about the visualization of population of orbitals. And first of all, we need to create our input files. And these are the input files that we need for non-adiabatic dynamics, and that is the RRR file, that is the output of the correlation code, and then energy pop file that we use for the geometry optimization calculation, and the master equation that is in the format of OS strength, that is the OS strength file in the matrix format, and then the band out file, that is the integration of per charge files, and this MATLAB code that we use for the charge carrier dynamics, and this is the location of MATLAB code. So for creating the master equation, we move towards the into the geometry optimization folder, and then we use we will create the input overlap file that we already have, and then we use this command to create the master equation, and then we convert this master equation into the master optics, and it will be in the format of this matrix as this figure has. And then the bandout file, for the bandout file, we create the folder and copy content from the geometry optimization. And then we use the postcard file from the previous geometry optimized cone-car file, and then we modify the in-car file, the number of bands and the energy energy intervals, and then we run the WASP. And after when we have the per charge files, then we use this Perl script. We need to modify, we can take the script from this directory, and then we need to modify the line 6 of the script in which we need to provide the information between the number of orbitals that we are going to use. And then we run the Perl script, and we got all these files we got the background file in that, and the results can be shown in this figure. So after that, we have the files, and we can transfer these files into the same directory at our local computer, in which we have the MATLAB code, and then we need to edit the input parameters in the MATLAB code that are explained by many previous speakers. And then we need to run the MATLAB code. And so this is the figure that is the output of this MATLAB code, and which gives us the information with time step how the electron move from the HOMO into the LOMO, and their difference in their energy. And the green area shows the normal distribution of electron and holes. That's it from my side.
Okay, please join me in thanking Amara. So, any questions in the room? Any questions on the line? Any questions in the chat line? So, Amara, there is a question in chat line. Will you please read and answer?
Yes, sure. Is the matrix optic file a matrix? Yes, this file is in the form of matrix, like this matrix.
Okay,
good.
It's not a matrix. The MATLAB code converts it to a matrix. It's just a line.
Okay.
It's not a big deal. It's just you mentioned it.
Okay.
Amara, would you please go to the last slide?
Yes.
So, would you please? Well, we plan to speak on the following subject again next week, but your diagram shows K sub E and K sub H. Would you share your opinion of what this notation stands for?
I'm not sure about it, but
Do not give exact answer. Just your impression, feeling. How do you interpret the figure? Like, what are these notations? What they point to? Just try to analyze as we go.
This can be the electron.
That's what you see by looking at the figure. Where the vertical line labeled as KE crosses the dashed line, dashed yellow line. At the beginning, at the end, or in the middle?
In the middle.
And how do you see, is it at the beginning of the middle, or at the end of the middle, or in the center of the middle?
In the center of the middle.
So just try to analyze try to give any suggestions, how can it be interpreted?
It can be when with the time step, the electron
Yes.
energy decrease.
Exactly. So it specifies average rate of energy relaxation. Yes. Perfect.
Okay.
Does everyone likes it, or there are more additional details how to tell it in different words? Yeah, it's good. It's good. Okay, more questions to Amara? Questions 1, questions 2, questions 3. Let's thank Amara once again. It's very valuable. And I have already forgotten our schedule. So the next presentation is by Lola. So Lola, would you like to share a screen and tell the story?
Yeah, can you see my screen now?
Yes, thank you.
Okay, so I will be speaking about the non-radiative dynamics, non-radiative relaxation. So I have a screenshot of the script here, but like the set of files that you will need to run this script are the energy pop, oscillator strength, input overlap, and then your RRR file that you are generated from the previous step. So here is where you impute the initial conditions. I usually would just look through the ones that have the highest oscillator strength and choose that. And here, it's clear that this file needs the energy pop files and the RRR. And here is where you specify your O min and O max for your structure. So what the results look like, first of all, you would get something like this, which specifies the frequency. I'm not very sure of what this frequency is. I know it's supposed to be like an angular frequency thing, but I don't exactly know what it is or like where it's coming from. And then you would also get like rate constants, I believe, for the electron and the hole. And for this is from one of my structures that I had. And here is where like the excitation started. And it's sort of like diminished, the intensity diminished before getting to the Omolola. So that's all.
Okay, Chris Granlie, thank you, Laura. So any questions, suggestions, or constructive criticism?
Yes, can somebody please explain this frequency?
Maybe would you like to try?
I'm not sure what that frequency was. I was just testing to see if I could get that to output as well.
Okay.
I'm not sure what that one is.
Okay, let's ask Landon, are you connected? Are you online?
I am still here, yes.
Okay, would you please teach us what is frequency, how it is related to your presentation? Maybe if Lola stops sharing, Landon starts sharing, and you can show which part of equation this frequency corresponds. It's also shown here.
That.
Yes.
Okay, so that's not what I thought it was then.
Lola, are you satisfied or you need more explanation?
What'd you say?
I'm asking Lola this.
Lola and I are sitting at the same table right now. So we're also talking to each other.
I wasn't aware of this. I'm just looking for confirmation of Ova if she's satisfied with the answer.
Yes, I am.
Oh, okay, okay. So the dynamics that we observe is a superposition of several eigen frequencies. And maybe Landon, if you stop and Lois restarts sharing her. And the rates KE and KH that we were discussing with Amara and that Lo is showing here, those combine all eigenrates that come from solution of eigenvalues, and depending on the initial conditions, this KE and KH will be different because combination of eigenstates for each initial condition will be different. This rates of relaxation is something that can be compared to experiment. It is one of the practical research. So, like if, for example, if I don't care about theory and just want to quickly compose something that can be of interest to experimentalists or to the editor of a journal, I can just systematically scan different initial conditions, find this KE and KH as function of initial condition, and discuss what this result is. So it's a minimalistic practical research that can be done with this tool to see response of the relaxation rate to initial excitation. Other questions, additional questions to Lola, or maybe question of Lola to herself or to everyone?
Could you go to your second slide? So I noticed there's a temperature variable that's set at 77 Kelvin, and then in the default file, there's a temperature of 1 Kelvin. Does that matter? Do we have to worry about varying that too much?
No, you don't have to worry about that. I mean, I don't think you don't have to change it.
Oh, okay.
Thank you, Hadassah. It's all same as Joseph. You are coming to the point. You are immediately finding the biggest places of the code. So may I ask Lola to stop sharing, Landon to start sharing, and go to one of because there are some important illustrative materials. Yes, write this slide. So the upper left. Yeah, maybe if you make your slides in presentation mode.
Yes, I'm sorry, I accidentally opened WebEx also, and that was getting in my way. There.
Okay. So this is RE. So it is a part of the Redfield tensor that is responsible for.
Oh, wait a minute. Sorry, this is you. This one is RE.
Okay. Who cares?
Yeah.
Yeah, please go to presentation slide so that we can see it a little bigger. Yeah. So first, it is segment. It is not the whole triple R matrix, but only a fragment that relates to pairs of orbitals in the conduction band. Second, if you look on the triple R matrix, you will see that it is large near the diagonal, zero away from diagonal, but it is symmetric in respect to the diagonal. Here, the illustration that Landon is making follows this pattern on the upper diagonal. So it's a substantial number on the first upper subdiagonal, and then it is zeros in the lower half of the matrix. So this upper and lower halves of the matrix correspond to thermally induced relaxation and thermally induced excitation. Like if the path is high enough, it may promote electronic states from lower energies to higher energies. And this detailed balance mechanism would depend on the temperature. If it is programmed properly, the lower half of the matrix will be non-zero. But for technical reasons, to avoid numerical instabilities that Joseph observed while setting it too high or too low. So to avoid these numerical instabilities, this part of the theory, this part of the code is simplified and postponed. So technically, the code is hybrid of couplings computed for real temperature. When we do molecular dynamics, we set up temperature, right? And it is our way to control temperature. The higher the temperature, the quicker the relaxation. But second part, there's the lower part of the matrix that Landon is showing should be non-zero, and it should be controlled by Boltzmann function. Here it is skipped because it creates more problems than solutions. But your question about setting up an explicit parameter for the temperature, if added, if the code is developed further, would affect lower part of this RE matrix.
Yep.
Yeah, thank you for critical item. Landon, thank you for sharing. You can stop sharing. Let's check if there are more questions to Lola. If there are, we ask her to share. If there are no, we'll go to the next speaker. So more questions to Lola once, more questions to Lola two, more questions to Lola three. Okay, please join me. Thank you, Lola once again. Okay, so the person who was asking the last question is the next speaker. So Hadassah, please share your screen.
All right, so there we go. So I'll be looking, I think some of what I'm talking about has already been discussed. But we're looking at the populations of these orbitals as a distribution over space and time. So last week we did the Redfield tensor calculations. This week we're looking at the dynamics. I followed along using the Matlab code. I also, like a couple other people, had some issues running my own examples. So if there's time, I'd appreciate any feedback on your ran too. But for this model, I did the same model that is the Amara Arshad was working on. So as also has been mentioned, an application of looking how these populations change in space and time can help you see how the charge transfer goes around. So in the MATLAB script, there's 3 big variables that help look at the populations and how they change over time. So one's is PPE, as it's called in the script. It's a list of the population electron states at some position at some time. This in the script ends up depending on your Homo and your max occupation level. There's this PE, that's a spatial distribution of the electrons, and this comes out of your band out file. And then WPE, it's a product of these 2 variables, which are matrices. And this ends up helping us analyze how the orbitals change over time. So I have another slide here to show like how this would look in equation form. So here we have our PPE, our PE, which is ends up being densities. I guess it's covered up on Zoom here, but there's a picture of like what it looks like in the code and line it's on. So once MATLAB has that, if you look at waterfall plots, this is just generating the command line what these all individually look like. So the first one's just this population, the second one is densities. The third one is just the runs initial like kind of like a skewed view of it, and then if you just were to do a top-down view, that's this right panel. This ends up being related to plots we get to see later, but MATLAB processes further before we get there. So after you have your WPE, for the final visualization of the graphs that MATLAB automatically generates if everything's working. It normalizes WPE, it extracts some electron data, then extracts hole data, and then it plots the data individually as electron holes or both electron and holes. So here is just the electron hole graph. Again, you see it similar to the raw WPE data from before. So this shows position on one axis, time over the other. Some general interpretation about what's going on here. This contour, or since this is a contour plot, you can, in MATLAB is a tool you can use to look at color bar on the side. The brighter values in this case correspond to electrons. The darker values, or the negative values in this case correspond to hole locations. If it's neutral color, what I understand that means that whatever was there in that place, the charge, or it didn't really, the charge density matched what it was before, so there wasn't really a transition. And this is the way you can see that over time, that charges move. So I guess in the case of this example, we have charges that end up focused more over here versus in these different positions. So that's all I have for this presentation. I'll leave it up for questions on this.
Okay, please join the second. Any questions in the audience? Any questions on the line? Yes.
One question with the graph we got up right now. How could you relate it to like the Homo levels, or like where you excite your electrons, where you put your holes? Or is there any way of like being able to tell that from this graph, I guess?
That's a good question.
I will make a comment wearing a hat of a mathematician. The answer does exist.
Yeah. I guess my guess would be here you have various bands. But my guess would be each of these would be like an energy level for the electrons, like, and then maybe the Amara Arshad would have to be individually checked out between each of these lines. I don't know.
Okay. So any additional interpretation? Okay, this question and this answer is one of the rare examples when realistic systems in the nature agree with our intuitive expectations about the models. So if you temporarily stop sharing, I'll start sharing and make an audio demonstration. So this is the data set from Keya, and the initial conditions for the example that was used as by everyone who tried. The electron initially is promoted from LUMO to LUMO plus 1, and hole is promoted from HOMO to HOMO minus 1. So both LUMO and HOMO, both occupied and unoccupied progression of orbitals, satisfy the intuitive expectations for the particle in the box concept. So if you look on the LUMO, the blue image here, so it has less density at the edges, more density in the middle. Second, LUMO plus 1 has less at the edges, more in about quarter from the edges, and less in the middle. So it shows this understanding that it is not a continuous particle in the box, but electron can stay only on the ions. So it's discretized representation of the particle in the box. And the illustration that was demonstrated is when one creates initial excitation of electron in the LUMO plus 1 where the density is in these two humps. And as time goes by, it relaxes and solidifies into the center. So we see how particle in the box concept experiences relaxation from first excited to the ground state for electrons, and similar pattern for holes. Thank you, Joseph. Thank you. Great question. I'll stop sharing. Hadassah, would you please share, and maybe there will be more questions?
So Dimitri asks third last slide, panel one, top left.
Well, it's not third, it's fourth. Like slide number 5 is counted for.
Please discard or interpret the image. We'll be able to obtain the same result with my pen and paper that computer. So, this represents our population of the orbitals. I think this this axis here corresponds to the band number or
Just number of orbitals.
number of orbitals.
Okay.
And there's only 2 shown here. So, I mean, I could,
So another axis is timeline, right?
yeah,
With time steps. So keep analyzing, because we all need to do it later for our practical research.
it kind of reminds me of the energy levels where you can see like a Homo low, well, that.
So it's Homo plus 1 and Homo, right? If it is for PB or electrons.
Okay.
Okay, keep going.
So you can, I guess it's showing Luma plus 1 relaxes. I guess you can see an exchange of the electrons or the electron population over time. So you go trades off between energy levels.
Okay. And second part of the question.
Could you say the same result given without a computer? I guess practically on a mathematical side, only so many electrons can be occupied on all the levels.
Like, can you get the same or similar lines without a computer? Like what do you need? Which equations you need to solve and how the solutions will look like?
I'm just thinking of things that could put you share electrons between energy levels. But it's not
So this system of equations. So rho 1 which let's name it as a unit like Luma plus 1 equation is losing its occupation proportionally to its original occupation. So we can just use variables that we like better. So dy dt equals minus constant 1. So how will you solve it and what is the solution?
integration. No. Or integration over time.
And what will be the answer? We don't need even pen and paper. It's solve it in the air.
It's just equal to the rate.
So what's the solution for y over time? Julia? Would you like to go and solve?
Yeah, I think so.
Okay, please.
Yes,
Y. No. Y is I disagree with your second. Okay.
Y squared by two.
Hmm?
Y squared by two. On the other side, and then we cancel.
And then don't we just have dy here?
What
Not like
should you transfer?
on the same side.
Oh, yeah,
So
yeah.
all unknown function on one side, all independent
Yeah.
function on the
I
other.
forgot about.
Okay. Oh, much better. Yes. Great. Okay, and how to make it y equals something? What should you do to the left and right part? Perfect. Thank you. Everyone agrees? Hadassah, does it make sense?
Yeah.
Do you have any maybe confusion or disagreement? Because this solution is by you exponentially decaying, and here it looks more like going in a theta function. So do you have any confusion or disagreement with how it looks there and how it is seen here? No, or do not hesitate.
Okay, sorry. No, I was just reading dy dt, and y was variable percentage.
So the images that we all are plotting with this code use time and logarithmic scale, and then this exponential decay looks more like a theta function. So it's just a trick to compress more time steps in a shorter window. But if you have only two levels, you don't need computer. We just take this R element of Redfield tensor from initial calculations and just solve it by finite way. So we need all this computerized technique only if you have like a lot of levels. Okay. More questions to Hadassah? More questions one? More questions two? More questions three? Many thanks. It's very inspiring and stimulated healthy discussion. So next presenter is Amir Keya. Amir, would you like to share a screen?
Yes, sure. You can see my screen, right?
Yes.
Okay, so today I think most of topics are covered by other presenters. We are going to talk about how to plot those green plot for relaxation dynamics and distribution of charge carriers in the space. So overall, the purpose of the implementing these non-adiabatic couplings, at least in my project, was to explore the charge transfer at the interface of a conjugated polymer and acceptor unit. Usually this blend will be used in the solar cell applications. So this method can be used to actually quantify their photovoltaic performance. And usually the system will be actually excited with the promotion of the charge carrier and based on the oscillator strengths, and then we will track the electronic relaxation, the rates, and also charge transfer. So, and this plot will be the conclusion of this method and this presentation, and we will review them at the end. So I want to a little more focus on the technical details, codes, and the needed files that we need to have those plots. So just as a review, we started with geometry optimization, heating, molecular dynamics, coupling calculation, and last week we review how to generate RR file, the elements of the Redfield tensor. Also, to finish the today calculation, we need to start again from geometry optimization. We need to calculate partial charges and calculate the band out file out of the partial charges. And at the end of this process, we will have energy pop for master optics and band out file. And together with RRR file, we will have the all input files needed to have those green plots. So the most important point before starting is that the range of the orbitals that you choose should be the same. Actually, that included the energy pop, but we should use the exact range for the coupling calculation and also doing the partial charges to generate the needed input files. So to have so we already have RRR, and to have the master optics and band out file, again, we need to have the concar file out of geometry optimization and use this incar file in the bin directory. And after running that, we will have those for master optics and band outs. This is the incar file needed to generate the partial charges. So you just need to specify the range of the energy of the orbitals. Usually you can find them easily in the energy pod. After running that simulation and finishing the jobs, you need to run this Perl script. So here again, you need to just the only things that you need to adjust in this script is to give it the range of the orbitals that you need. Again, exactly should be the same, the range of the energy pop. And at the end of this process, you will have the band out file. Also, running this 3 steps will give you the 4 master EQ that you can copy it and save it as 4 master optic. So again, before doing the calculation, make sure that check the size of the input files. So energy pop for master optics and band out. So this first number of this should be the same. Actually, it's equal the number of orbitals that you perform the coupling calculations. So we have 4 input file here for master optics, band out, energy pop, and RRR. And now we can perform this MATLAB code. I just a little tweak that and add name to it, summer 2022, but you can also use the original file. So in this file, I a little change it. So the only thing that you need to specify is the initial transition, cell size in the Z direction, and also number of time step that you perform in your simulation. And so the initial transition will be based on the oscillator strengths, which give you the highest probability of the excitation for that transition. For instance, here for today's result, we can see the transition from Homo -3 to Lumo +2, which is the second highest oscillator strength value. But usually you should repeat that for multiple oscillator strengths. After running the MATLAB code, it will give you some numeric value as KE and KH, which are relaxation rate of the electron and holes. In previous presentation, we reviewed them. And this 2 panel will be the outcome of this section. So first, an electron is promoted from Homo to Lumo. System is excited based on this initial transition, and as time goes, we can see that the electron, the yellow color, cascade down on the Lumo orbital. Sorry, this is a typo. It should be a Lumo, and also this hole will stand on the Homo. And also here we can see that the distribution, a special distribution of the charge carrier in the Z direction of the cell size. You can see that at the end of the simulation, electrons will relax on the acceptor unit and holes on the backbone of the conjugated polymer. Also, another interesting outcome of this kind of calculation will be quantifying the charge carrier. So from difference of the expected value of the charge, actually electron and holes, we can have the dipole. the definition is presented here. And by definition also, the slope of the dipole moment over time will give you the current density. So here we use this equation and this results to quantify the current density. So the system that give you the highest current density usually is expected to have a better photovoltaic performance. And yeah, I would be happy to answer your question, if any.
Okay, please join me in thanking you. So any questions in the face-to-face room? Any questions in the from the online audience? Any questions in the chat line? It looks like it was so interesting and crystal clear that everyone is impressed and speechless.
Or maybe so tired to ask questions.
So, okay.
Thank you.
Sentimental compliments. Okay, let's count down just in case. More questions. One. Dinesh, do you have any questions, Pamir? Anyone wants to challenge him on the charge density, on the current density? More questions one. More questions two. More questions three. Let's thank Pamir once again. So we have two more, but they are of special importance. So Sarah, you can start sharing. Everything we did up to now was done for even number of electrons for single configuration. But if the system has unpaired electrons, various transition metals, magnetic materials, one may need spin polarized calculations, and then codes are noticeably changed. And Sarah will teach us what to take into account if we deal with, if we eventually need to deal with spin polarized calculations if you go away from singles. Okay, Sarah, the floor is yours.
Okay, thank you, Dr. Klein. So as Dr. Klein said, I'm going to talk about the same procedure, but with the case of a spin polarization. So firstly, we need the RR file, which is kind of different for the spin up and the spin down. So we need to create another two directories, so called up or down or whatever you want. Then you need to copy the RR file into each directory, and you need also the par charge files in order to extract the dynamics for each of the spin up or the spin down. So after creating the partial charge files, as previously speakers explained, we need to execute this Perl script. Actually, we need to first copy it and then execute this. This script let us to extract the dynamics for the spin up and again for the spin bed actually separately. So before executing this command, you need to specify the range of orbital. So actually we need to modify the Perl script as I shown in the below. So just insert the desired range of the orbital here, and then launch the script by just type Perl and the name of this script. If everything goes well, finally you end up to two files. One is band out diff, the other is band out sum. Actually, I think diff means for difference between the alpha and beta, and the sum is summation of the alpha and beta. So in order to run the MATLAB code, as others said, we need our file, band out diff, band out sum, energy pop, for master equation, and the name of the MATLAB code. Here, in this case, is Redfield spin up, for example. So in the MATLAB code, you need to specify the cell size, the Z step, Homo, LUMO, and the range of orbital you want. So mostly we take the transition with the highest oscillator strength, which is the third column of the OS strength file. So, and then you need to specify the transition range, like IH and IE for the Homo, for the hole and the electron. So IH equal to 1 means the Homo. If you change it to 2, it means Homo minus 1. If you change it to 3, it means Homo minus 2, and so on. For the IE equal to 1, it means the LUMO, and equal to 2, it means LUMO plus 1, and so on. So at the end, if your MATLAB code runs successfully, you will see the relaxation rate for the electron and hole, and two figures which shows the energy dissipation as a function of the time and the charge carrier distribution in the space in the right panel. So in this case, you can see that the hole relaxes faster than the electron. That's it. Thank you.
Okay, let me thank not everyone for taking the color. So any questions in the room, in online, or in the chat line? Sarah, may I ask?
Yeah, sure.
Oh, thank you. So from the first part of the talk until this slide, it looks like you need to have two directories with two data sets.
Yes.
So the part of the system with alpha spin, with spin up, and part of the system with spin down do not interact with each other and should be treated as independent models in different directories.
Exactly.
Same
Yeah.
thing.
Yeah, we need to repeat the process 2 times. One time is for the spin up, the other time for the spin down. And the files that you copy paste in each directory have different kind of material. For example, the RRR file for the spin up is different from RRR file for the spin down, as well as energy pop. Everything are different.
Okay, thank you. But your last slide, can you please go there?
Sure.
Yeah. It shows one green diagram for energy relaxation and one green diagram for distribution in space.
Yes.
Is it for spin up or spin down, or is it combination of both? Like I was expecting to see a second set of images for different spin. Can you comment on this?
This one is just for the spin up as an example.
Okay.
So yeah, I didn't get your second part of the question.
And if you do similar, if you just keep going similar excitation energy for spin down, would it look same or different?
No, different. I think it should be different. Yeah.
Okay. So can you send to the chat line maybe link to your paper where you show the difference of spin up and spin down dynamics? Because it can be interesting for if someone is interested in seeing this difference, it could be valuable.
Yes. Just give me a second to stop share.
So while Sarah is making this, sharing the link, let's check if there are questions on spin polarized dynamics. If anyone is looking to discuss, or maybe I feel that Dinesh may ask what will be the specifics to make dynamics for triplets, for doublets, Did you want to ask it to Sarah? Or is enough for now?
Specific question now.
Okay, yeah,
I may ask
okay, yeah,
later.
okay. So let's count down more questions one, more questions two, more questions three. Many thanks, Sarah.
Thank you.
It brings additional dimension to all of our research. And the last but not least, the presenter is Dave Faulkner, and he goes even more wild. So he goes into a situation when system may experience spin fluid, when the spin configuration may change between, let's say, singlet and triplet, or even something more exotic. And David will teach us which specific modifications of the codes and the input files need to be done to deal with non-collinear spin calculations. Okay, floor is yours.
So we're looking at the MATLAB code that we've been looking on. There is a different version for spin orbit coupling, which is the really long MATLAB script type name there. You can find it in the bin on NERSC, at least on NERSC. I think I added both NERSC and Photon bin, assuming Photon's working.
Should be working.
You also need the four master optics, the RRR, the band out, and the energy pop, of which about the last 6 people have all covered how to make. So if we look at the actual input file, you've got these 3 areas that I have boxed. Those are the major things you need to worry about. So the red is the HOMO and the OMIN, OMAX. And those are going to be your orbitals. And you have the blue, the initial conditions, which have been described. So in this case, we're looking at HOMO -5 to LUMO +10. And in the green box, we have some parameters for the z-axis. The major thing you need to worry about, especially if you aren't worried about getting the dynamics by z, the major thing you need to worry about is z steps, because the code will fail if z steps isn't set up to be equal to the band out with regard to the band out. So then if we look at the results here, so I have, you can see that you get the KH and KE, and then I have the waterfall graph or the occupancy graph, and off to the side here, you can see the code that actually generates this graph. I included the code that generates both the hole and the electron graph, although I'm only showing the whole graph. So the major thing is this waterfall, which is describing the type of graph that it makes, and then the PPE or PPH, which is the population of the hole or electron, which was discussed a couple talks ago. And then here we have the non-radiative dynamics plot, which is the green fig. And then you have, this is the portion of the code that actually generates this plot. So we can see that if we look at it, so the yellow is the value of the electron, with the dotted line being the expectation value of energy. The solid line is the expectation value of energy for the hole, with the blue being the hole, and then the green is the background.
Okay, thank you for being short. Who's joining and thanking David. So any questions or anyone wants to either give sentiments or challenge the speaker.
Now question.
Yeah.
Why we need a different set of Matlab code?
I don't honestly know. I have gone through it a little bit and all the math I've seen is very similar, but I haven't gone through it entirely to compare them. The major thing that is different is going to be dealing with degeneracies, which I don't know if there's any point in this code that we need to worry about degeneracies. Trying to think through, and I don't think there is at this point.
But your idea is to unify and have just standard release of the code, which will differ only by input parameters, either spin less or spin orbit couple.
Yes, because I guess we treat couplings differently, right? But I
Yes.
guess,
Yeah,
how does that,
after that, it's, as far as I know, identical, outside of some minor figure differences
Yeah.
between versions. Which it actually, the figures are really, this version of the code makes doing the figures kind of annoying. You see that the waterfall graphs are actually commented out in this picture. That's because if you have them, the code is set up somehow that if they are in, the code stops after the waterfall graph. It won't generate the green fig or the blue figs. If you have the waterfall, if you have it set up to make the waterfall graphs, and I've not figured out why. I am working on rewriting it to make it a little more streamlined. But I have not gotten to the point where it's ready to actually do anything. I'm also working on adding Aaron stamping protocol, which Lola used to it as well. And there is some look that it might actually be set up for the 2D orbitals. Which I am only starting to work on, so I'm not entirely sure exactly how those work yet.
Do you think you'll be able to show 2D orbitals next week?
I am hopeful.
Okay. And consult London if needed. So he might have some memories of this. London, do you remember how you worked on two-dimensional slices of orbitals of partial charge densities?
Yes, I don't remember all the details, but I do remember, having done it.
Yeah. We need to bring this competence back to group, and David is focusing on it right now. So maybe
Okay.
he will like to contact you, maybe not. So what Dr. Khan, what we will ask David sparks possibility of effort which goes along from science and more to the business side. Maybe we can make a little, well, it's all non-monetary, but pseudo company that generates a pseudo commercial code. And then we set up a virtual place like in a cloud or on a server where everyone has access. And on personal computers, we debug code, but if we see that there is a absolutely necessary change, we just, as a group, co-edit primary version of the code, agree that just it will work and matches any conditions, and then announce the release, at least inside the group, and maybe if you want global supremacy to outer world.
So like GitHub,
Yes.
Haley has already convinced me of it, so I really that suggest it here.
Thank you.
Can I answer your question, Julie?
Yes.
Okay, any other questions?
Thank you. It's more than a question, it's a suggestion of new chapter.
Because I got one, your second slide, you have Z half box. I know what Z step, C sizes, what's Z half?
I have no idea what the Z half does. I've not honestly ever looked at through the code to find out what it does. I've never changed it.
Okay, you don't.
David, I have another question, the same question, maybe with 2 lines above. What is the role of this voltage? Always I can see it in the codes, but never use it.
So that my knowledge adds a voltage parameter, which is we basically never do.
So Landon and you may answer if they want.
Because it's part of the field variable, which is then used to determine some stuff with energy power. But I've personally never used it.
Amir, thank you for asking the question. I believe you're asking it because you're interested in photovoltaics, or one looks for current as the response to voltage. Maybe it's attracted your attention. So several years ago, London started a project and then did different things, and then Dr. Khan continued. So the dynamics under the voltage shows very different features. Basically, it is all sparked by interest to photovoltaics. And there are 2 ways to take it into account. One is to literally use electric field in the VASP, so just recompute energetics, like energy orbitals and couplings under the voltage. So in the VASP in car, one can, there is a keyword that adds voltage, like E field equals and then vector of 3 components. The other thing is to keep the orbitals compute and couplings computed for no voltage, for 0 voltage, and then do some artificial correction. Because upon voltage, it just shifts in the first order perturbation theory, it just shifts the energies of each orbital compared to their center of the charge. Landon, would you like to add something? No, that's perfect. Okay. Amir, are you satisfied?
So it is already applied in the codes. So if somebody change just the voltage parameter, it will influence the results correctly.
I think it is just a rudiment as a trace of previous experiments. The version of the code that accounts for the voltage is different and is in a different repository. But if you're interested, it is very possible.
Thank you.
And this half size, right now it is not used, but I think it is done in case one needs to find specific observables for also related to charge transfer. Let's check if there are more questions or maybe typed questions.
Dimitri asks, what are the absolute numbers of Homo orbitals in NCS SOC calculations in comparison to spin polarized calculations? So the SOC calculations compared to spin restricted have double the orbitals compared to spin polarized. If you are to consider spin beta and spin alpha as different orbitals, it would be the same. If you consider them the same, it would also be double.
So if it is, if one applies it to singlet, then basically Homo spin orbit will be twice Homo spin polarized.
Yeah.
If it is like higher multiplicities, it may slightly change by 1 or 2.
Keya asked David, why did you use IH equals 6 and IE equals 11 instead of using IE equals 6? IE equals 6, he used different values. So is there any reason behind that? I have 2 possible answers. This was one of the first models I did this on. I honestly don't remember specifics. So it is either the highest oscillator strength or random numbers I picked when I made this originally. If I don't think I have it open.
Okay, let's, Keya, are you satisfied with the answer?
No.
So can you verbally tell what else do you want to hear?
Yeah, like I think it's not a correct, like maybe it's partially correct that you choose randomly, but obviously there are other reasons as well. If professor explain these things, that will be great.
So why you think he should use IE equals 6K?
So this one is from the same model. This is from my Sanibel poster. This is from the same model. This one would be the highest oscillator strength one. So this is, I probably picked numbers when I was screening randomly, and this is what I saw. Because when I made this, I probably was just trying to get a figure that I could put on it originally. But as to why I'm not making them even, it's pretty common for them to not be even if you use oscillator strength as your basis.
Okay. Let me add, because if K is not yet satisfied. So the experimental conditions specify only the excitation energy. But the experimental conditions do not tell which specific electron and which specific hole is excited. So what we do, we apply ground state DFT for optical properties, which is not a good thing. It's also Forstmann argument. It's just because it is so much quicker. In any appropriate methods to describe excited states, the excited state is a superposition of several electron hole pairs. So if we graphically have this much of excitation, it can create qualitatively different situations. So first, hot electron, when we remove, create hole on the Homo and create electron higher up in the conduction band. With the same energy, we can create a hot hole, or we remove electron, create a hole very deep in the valence band, and create electron on the lumen. Or we create, we can excite in like midway from valence band to conduction band. So if you would base our calculation not on the DFT, but on TDDFT or RPA or our initial excitation will include superposition of all three. But right now, we do need to go over individual excitations. And the question that Kay did ask, I would never ask this question myself. I would just practically, I would probably reformulate it in the following way. Why don't you scan and show us several initial excitations? Because just to see properties of the system, one needs to scan all of them and see how the system responds to them. But one individual excitation costs nothing, or it's only one demonstration example. To learn more about the system, one needs to scan through multiple excitations. And the symmetric, which looks beautiful for humans when electron and hole are equally deep in valence and conduction band, is only one situation. It is on the equal foot with hot hole and hot electron. Okay, are you satisfied? More?
Yes. Now it's clear.
Okay, thank you. So more questions today. Questions one, questions two, questions three. Many thanks to all speakers and contributors to discussion. We will have one more knowledge transfer session where we will either repeat some key things or go a little bit more deeper. So we will go deeper into what Amir taught us about charge transfer, and we will open a new little chapter, which may go a little shorter in time, photoluminescence, which is a challenging question in itself, but it is another part of the code that we all are already running. So it was just too much for one meeting. And then after we are done with next week, we will be ready for going into more standard practice for all participants of this club. We'll do just research update, and the rest will provide very friendly criticism. So many thanks for, I will provide subjects for sign up, not immediately because we all are probably exhausted, but no later than Sunday night. I'll try as early as I can. And many thanks to everyone. Meeting is done. Everyone is welcome to disconnect and to depart. I'll stay both in the connection and in the room if brief discussion is needed, but formal part of the meeting is done. Many thanks once again.
Thank you. Yeah.